Good afternoon. Welcome to the last day of new material for AP Statistics. We're in the 10.4 handout, Inferences for Regression, Part 1 of 3. Remember, the big idea here is we want to find, either build a trap for the true regression slope, beta 1, or we want to calculate a p-value. The null hypothesis all the way through is going to be that beta 1 is equal to 0. There's no association between these two quantitative variables. The alternate hypothesis will be that the slope of the line of best fit is not equal to 0. Let's jump into our first example, number 1. It's the 10.4 handout, open to hurricane predictions. And way back in chapter 7, whoa, that was unit 3. Way back in unit 3, we looked at data from the National Oceanic and Atmospheric Administration about their success in predicting hurricane tracks. Here is a scatter plot of the error in nautical miles for predicting hurricane locations 72 hours in the future versus the year in which the prediction of the hurricane occurred. Okay, so years since 1970. So by the year 2000, the 72-hour error looked like it was coming down. Here's the line of best fit. You want a good example of EVA, equal variance. This is not equal variance because we have a lot of variance way back in 1970, but then the variance shrank. Basically, the predictions got better. So the equal variance assumption is not justified because the does the plot thicken condition fails. The plot thickens as you move from right to left. It thins. The plot gets thinner as you move to the right. So it's a great example of the failure of the does the plot thicken condition. In chapter 7, we could describe the relationship only in general terms. Now we can learn more. Here's the regression analysis. So on Monday's test, I've moved the test to Monday, you're going to get a printout. And what you're going to see in the printout, several key things. I'm going to circle them in white because it's be easier to see. You're going to see the t ratio, the p-value for the intercept. And keep in mind that no one cares about the intercept. So you'll basically be ignoring the p-value for the intercept. The only p-value we care about is for the slope. So this is lowercase b0, here's lowercase b1, the sample slope. This is the slope that came from this sample. It's not every single hurricane since 1970, it's just this sample. The scatter plot represents a sample of those. So here's the one we care about. And the slope, the sample slope was negative, and the probability that we observe a slope as negative as this one or more negative this one due to just natural sampling variation alone in samples of the same size is super low. Therefore, we would end up, based on this p-value right here being less than 0.05, this is the basis on which we would reject the null hypothesis. It wouldn't be this one. We ignore that one. No one cares about the intercept. We care about the slope. And it looks like the slope is in fact not equal to 0. So, in context, what does this regression say? Well, I'm gonna fast forward 1, 2, 3, 4, 5. Just 2. Oh, that's interesting. That is the set of answers, which I want to give you a chance to record. What it means is that the equation of the line of best fit for these data points is, and I'm going to circle again, here's the intercept, here's the slope. So error hat. Don't forget about putting the hat on the dependent variable. How do you know it's error hat? It's because the dependent variable is listed up here. The other variable is listed right there. So instead of y and x, and instead of y hat and x, we have error hat and year since 1970 condensed to year. Here's B0, here's B1. How many of you remember looking at tables like this in the past and writing equations in the form y hat equals B0 plus B1x? Same thing here, except now we're actually going to, in the past we saw this column, but we didn't know what it meant. We didn't know about William Gossett, so we didn't know anything about the student's T model. We didn't know about p-values, and we didn't know that the standard error of the sampling distribution of sample slopes is approximately the standard deviation. So we only paid attention to these two numbers in those two words. So that's review. According to the linear model, the error made in predicting a hurricane's path was about 453 nautical miles. So back in 1970, the error, we were off on average by 453 nautical miles. And the, one more thing, 10.4, yep. Okay. Now, this phrase, on average, is an easy one to leave out. The idea here is that it could be more or less than that. It's going down the line of best fit, started at 453. It might be more than 453 error, it might be less than 453 nautical mile error, but the line of best fit shows you the average error. So that's why we need that phrase, on average. The error has been declining at a rate of about 8.37 nautical miles per year. So that's what it means. Now, if I were to give a more scripted answer, it would be, according to the model, the predicted error in the hurricane's path in 1970 was about 453.22 nautical miles on average for each additional year. And there's that phrase, you remember the video of me feeding ham to my dogs, for each additional hour of flood duration is what it was back then. Here it's for each additional year since 1970, the predicted error decreases by about 8.37 nautical miles. You've got that scripted one already filled in. So, next page. Here, we're going to state the hypotheses about the slope, and your hypotheses, I believe, are filled in for you. Notice how it's worded. The parameter is beta 1. It's not B1. It's beta 1, the true slope of the true regression line. We assume it's equal to 0. The alternate hypothesis has the does not equal to symbol, which means there's been a change in prediction accuracy. So it's the same table. In part C, we see assuming that the assumptions for inference are satisfied, which is probably a bad assumption because AVA is not justified. Equal variance assumption is really not justified, but we're going to assume it's okay anyway, even though it's not. So the model, assuming the conditions have been met, the sampling distribution of the regression slope, that's new language, but the regression slope has its own sampling distribution. It can be modeled by a student's T model with, it's a new formula for degrees of freedom. Instead of n-1, it's n-2. Why? Well, in part because there's two dimensions. It's not a one-dimensional distribution. It's two-dimensional. We have two axes, so instead of n-1, it's going to be n-2 is the degrees of freedom formula. We use a regression slope t-test. So that's the name of this test. It's a regression slope t-test. The mechanics are thankfully performed by computer, so you don't have to fill in mechanics. However, just so you know, where did that t ratio come from? Try this. Do me a favor. Take negative 8.37084 on your calculator. Go ahead, type that in. Take the coefficient and divide it by the standard error. negative 8.37084 divided by 1.209. And that we do expect you to do on Monday's test. Because we might not give you the T ratios, we might expect you to take column 1 divided by column 2 to get column 3. And then you would have to use, to get the p-value, you'd have to use TCDF of negative 6.92, comma, and how would we do that? It would be, yeah, you wouldn't start with negative 6.92, I can assure you of that. Yeah, that's a little tough to take. I just erased the entire page on which that. So 10.4, I'm just going to reopen it. Open recent 10.4, 17, 18, and it's back. So anyway, hurricane predictions. So we're back. We were on this page, right? So the thing I was saying about TCDF was that if you wanted to get this second p-value, you'd have to take 2 times, try this, TCDF of negative 999, comma, negative 6.92, comma, 32 degrees of freedom. That's how you end up getting a number that's less than 0.0001. Can someone explain to me why there's a 2 out front? Why am I multiplying this by 2? Amelia, go ahead.
It says does not equal.
It's 2 tail. So it's because it says does not equal 0. That's why. That's exactly why. It's because of this guy right here. So anyway, that should line that up. Now, the value of t is negative 6.92. It's probably that we observe the association of the data due to chance alone, given that there's no association. So that's how to write the interpretation of the p-value. And keep in mind that an interpretation of a p-value is always optional in the conclusion. It's a good thing to think through, but a conclusion never requires that you interpret the p-value. It's just good for the brain to think through that. So here's where you actually have to start the conclusion. Since p-value is significant, alpha 0.05, and very low, we reject the null hypothesis. There is strong evidence that the prediction accuracies have in fact been changing during the time period. By the way, R squared is a review from semester 1. 58.8% of the variation in the prediction accuracy is accounted for by the linear model based on year. And that R squared value of 0.588 was in the table. See it there? R squared, 58.5%. It's on line 2 of the computer printout. Now, I would like to draw some things for you back on the previous page. Something that I'd like to draw for you looks like good shape. Okay, so go to the previous page.
Right.
And I got the old, you know what? I'll give you a little more time. Yeah, question.
What is SE coefficient?
It's a standard error of the sampling distribution of, for the first one, it's of sample y-intercepts, and the second one is the standard error of the sampling distribution of sample slopes. So,
what are they measuring from?
they're measuring based on the given sample slope. Now keep in mind, and that's why I wanted to draw a picture for you. Go back to the previous page. Draw this line of best fit. That's just one line of best fit. If I took another sample, I may get a line of best fit that looks like this. If I took a third sample, the line of best fit might look like that. Different intercept, different slope. A fourth sample, I might get a line of best fit that looks like this. Every sample generates a line of best fit that has a different slope and a different intercept. So there's a sampling distribution of sample intercepts, B0, and there's a sampling distribution of sample slopes, B1s. Those slopes have a standard deviation. They have a mean and a standard deviation. We're not going to be concerned so much with the intercepts, just primarily the slopes. So that's important in terms of interpreting. This is Caleb's question. You know what this means, this 1.209? That means that the typical difference between a particular slope and the mean slope is about 1.209 nautical miles per year would be the units on that. So this is the standard deviation of these slopes. That's just one slope. It's like, so if we had a standard error of like 0.003, it'd be like, wow, our sample's like really close. Our sample slopes are really super close to the true slope. So, but there's another S, here's another standard deviation. This S right here, that's the standard deviation of the residuals. So, standard deviation of the residuals, and then there's another standard deviation of the slopes. Okay, now, we've never drawn sideways bell curves before, but if we're hoping for that all year, today's your day. Because what's going to be the error in hurricane prediction accuracy 7.5 years after 1970? Well, the idea is that draw a sideways bell curve. I mean, there could have been a whole bunch of hurricanes in 1978. 1976, 7.5 years. So, 1975, 1976. Some of them in the year 1976 will have really high errors. Some will have really low errors. But the average prediction error is on the line of best fit. So, notice that 15 years after 1970, the sideways bell curve, basically saying, okay, so that's like 1985. 15 years later, 1985, some of the hurricanes had predictions that had really big errors, some had really small, but on average, this is the average error. Basically the y-coordinate of the point on the line of best fit. That's the average error in prediction. So notice that the line of best fit really it contains all of the means of the sideways bell curves. So it's important to realize that these scatter plots are made up of, the lines of best fit are made up of the means of the sideways bell curves. And the mean of the prediction error has been coming down. So this is another way to answer your question, Caleb, because this standard error of 1.209, that's supposed to be the standard deviation of the sideways bell curve. And okay, so I know you're thinking, wait a second, so you're slow. That is actually what it is. It's a standard error. Does that surprise you, or does that confuse you? To say that's so these, I actually, when I said that, residuals, I just realized that I was messing up these two standard deviations. It's actually, this one is the standard deviation of the sideways bell curve. This is just a standard deviation of these slopes. And we don't have the slopes graphed. So I take that back. I take it back because this is, these residuals have a standard deviation of 75.38. So 75.38 is the standard deviation of the sideways bell curve. This is just a standard deviation of the slopes, which do not have a nice connection to the graph other than to think of a whole bunch of different lines of best fit. It's these different slopes that have a standard deviation of 1.209. So these sideways bell curves have a standard deviation of S equals 75.38, which can also be thought of as the standard deviation of the residuals. I mean, in the year 1985, there's some hurricanes have prediction accuracy, they're like right on, very low residual. Some were really high residual, but the standard deviation of the sideways bell curve is what this S is. Yes, go ahead.
How can you have a mean of best fit lines? If it's a best fit, doesn't it fit best?
Yeah, it fits best. This scatter plot But this is only 34 hurricanes. I'm sorry, it's only 36 hurricanes, right? 36 hurricanes. Believe you me, there's been a lot more than 36 hurricanes from 1970 up to the year 2000. If we picked a different sample of 36 other hurricanes and looked at their prediction accuracies, we'd get a different scatter plot and a different line of best fit, which would have a different slope and a different intercept. So if you imagine all of those slopes from like all possible different samples of size 36, those slopes would have a standard deviation of 1.2. So yeah, this is the line of best fit for this particular sample. And if you were to go back and use it, then let's say we use this line of best fit based on this sample. Let's go back to the year 1985. We could use the line of best fit, Amelia, to predict what the prediction error was, the predicted prediction error, because hat means predicted. So it looks like the predicted prediction error was about 375 nautical miles. But some of the hurricanes back in the year 1985 would have had even more error. Some of the hurricanes back in 1985 would have had even less error. This is just the average error. The predicted prediction error from 1985. So yeah, the concept does get deeper, and we're going to have to be able to explain that. So that's why I wanted to take a lot of time with that, to make sure you understood the two standard deviations. And man, Caleb, I'm so glad you asked about what this standard deviation is, because that led to me making a mistake on interpreting that in terms of the graph, so that we finally got it locked in. This is the standard deviation of the sideways bell curve. This is the standard deviation of the slopes. Let's go to the next page. So we've got, the next one is movie budgets, more sideways bell curves. Let me tell you. Movie budgets, how does the cost of a movie depend on its length? Look at that scatter plot. This is not all the movies released in 2005, but it's major release films. And they're summarized in these plots in computer output. So we're just taking 2005 as our sample. These are the major release films. Looks like maybe, I mean, it looks like a random scatter, but maybe it's the kind of thing where, let's see what it is. -31 is the intercept, the slope. It's going up like that. So everyone wants to get ahead and start on taking the notes. But is it true that the longer the movie, the more it costs, the bigger the budget for it? What's this movie over here? Maybe this was like the Blair Witch Project or something, where they did like this whole big long movie on a handheld video thing. It's like hardly any budget at all. You don't even have to pay the actors that much. It's basically, they're making it for essentially $0. You just have to buy a video camera and pay a few people. Okay? Now, I didn't watch the Blair Witch Project, but I heard it was like the first, big major movie that was filmed on a handheld video camera. You said you didn't watch that movie, did you? I don't even know if that was in 2005, but there was apparently some movie that was longer than 3 hours that cost almost nothing to make. All right, and then of course you've got some movies that are really short movies, less than an hour and a half. Are you kidding me? This movie's like 3 minutes long, and still paid $20 million to make it. Yeah, it's actually 2090, so actually it's about an hour. It's a 1 hour movie that was fairly expensive. But notice the intercept is -31. So what this means is that what are the units cost in millions of dollars. So if you want to make a movie that's 0 minutes long, it'll cost you -$31 million, which means you get $31 million. That's it. How often do you learn stuff like this in school? You just found out, oh, man, I don't ever have to get a job. All I have to do is make one movie that's 0 minutes long, which that shouldn't take too long. 0 minutes and 0 seconds, and I'll get 31 million. Someone will pay me 31 million. How exciting! No, that's just what the model predicts. That doesn't mean that's what happens in reality. Okay, that's just it's the model happens to have an intercept way down there at -31. It would be an extrapolation to actually predict the budget at time zero. But the model predicts that for each additional minute of runtime, the cost of the movie increases by about $714,000. Oh yeah, let's just make the movie 1 minute longer. Oh, do you have $750,000 for each additional minute? Okay, now, keep in mind that on these problems, you don't have to do any calculations. There's no buttons on the calculator. There's no A, B, 80, 56, 24, CD, donate your card today, A2. No, there's no jingle. It's all given to you. All you have to do is look at it and read it. So the intercept is negative, discuss its value, taking note of the p-value. The negative intercept makes no sense, but the p-value of 0.07 indicates that we have a C. Check that out. The intercept, if someone were to do inference on the intercept, null hypothesis is that the intercept is whatever. Okay, the point is, we don't have reason to believe or to take the intercept seriously anyway. But we don't really care about the intercept. What we care about is the slope. So the intercept usually doesn't ever get much attention. So, anyway, the fact that the p-value is not less than 0.05 indicates that we have insufficient evidence to discern a difference between our estimated value and zero. The statement that a movie of zero length should cost $0 makes sense. Yeah, if you want to learn anything in school today, learn this. Movies that are 0 minutes long will cost $0 to make. Yes, go ahead, Paige.
So is the only reason we paid attention to the 0.07 p-value because it asked about the intercept? I just want to make sure.
Yeah, sometimes they might comment. I mean, occasionally AP tests will be written in which they ask you to say something about the intercept.
Okay.
And, does it make sense in reality? But that's somewhat unusual.
Okay.
So moving on, we've got some more stuff here. So the output reports S is 32.95. So here's a new script for you. Here's a script that we haven't ever had to make come out of our pens or pencils before. But they're going to ask you to put S equals 32.95 into words. Remember that the concept is standard deviation of sideways bell curves. Draw a few sideways bell curves simply because some of you have never drawn sideways bell curves before. You need to practice that. And S is the standard deviation of the sideways bell curve, but they're not going to accept that statement on the AP test. You can't say, oh yeah, 32.95 is the standard deviation of the sideways bell curves. Which, by the way, that's why they need EVA, the equal variance assumptions, because we're assuming that all the sideways bell curves have the same standard deviation. If the plot is thickening or thinning as you go, then that won't make sense anymore. But here's how you put it into words. The output reports S equals 32.95. What that means is that for films with the same runtime, so it's like you have to take all films of length 90 minutes, or all films of length 120 minutes, or all films of length 150 minutes. For all films that have the same runtime, which means if you lock into one of the sideways bell curves, then the amounts by which costs differ from predictions made by this model vary with a standard deviation of 33 million. So there it is. There's your first example of how to get that concept of a sideways bell curve's standard deviation into a sentence. Do you have that phrase for films with the same runtime in there, or do you have to add it in? Yeah, I think you have to add it in. It's the phrase in red here. That's why I put it in red here in the notes, is because I knew that it wasn't on your copy. So your answer to question C would be, it would start with the phrase, for films with the same runtime. And the reason you're writing that is because you want to lock in on a particular sideways bell curve. The amounts by which costs differ from predictions made by this model vary with the standard deviation. Okay, what's the value of the standard error of the slope of the regression line? Okay, that's just reading it right off the table. SE, that's the SE column. The standard error of the slope is the 0.1541. So you're going to have to look at the table and write it down. The standard error of the slope is $0.1541 million per minute. And explain what that means in context. What it means is that if we constructed other models based on different samples of movies, we'd expect the slopes of the regression lines to vary with a standard deviation of about 154,000 per minute. Notice the units, these slopes, they are rates of change, so they have to be written with dollars and minutes as their units. So that's another page complete. Let's go to problem 5, movie budgets, the sequel. Get it? All right, let's go to the sequel. When are we going to look at the prequel? That's my question. I don't want to do the sequel yet. Okay, so here's the prequel, the sequel. All right, if you're actually going to do this essay and use the acronym that we learned 2 days ago, LINE, L-I-N-E, you would have to write about the linearity assumption, L, I for independence, N for normal population assumption, E for AVA, equal variance assumption. Does the plot thicken, etc. So I just wanted you to have just, notes on how to do that. The mechanics, we're trying to build a beta 1 trap. And if you want to construct a trap for the true slope, then let me zoom in on this for those of you watching on YouTube. Here's what you would write. It's probably printed right there for you. The sample slope plus or minus t star sub n minus 2 degrees of freedom times the standard error of the slope. So the observed slope from the chart is 0.714. Just verify that you know where to pick out the 0.714 from the chart. You need t stars of 118. And here I'm asking my students not to just write down t stars of 118, but to actually write down what that number is. And t stars of 118 comes from inverse t. And what is they say what the, 95% confidence interval. So when you're doing this, to find this number, t stars of 118, you would have to type into your calculator inverse t of 0.975, 118 in order to find that number. But and there is no button on the calculator that will actually automatically generate these teeth. So let's practice the calculator work now. On your calculator, type, in fact, I'll pull up my calculator right now. We'll do it together. To find these teeth, you have to do actual calculator work on the home screen. So you'd have to type in 0.714 plus inverse t. I'm going to go to the distribution menu, pick up inverse t, of 0.975, 118 degrees of freedom. Because there are 120 movies in the sample, we subtracted 2, times the standard error, which is given as 0.1541. So those are the teeth on the right of the beta 1 trap. If I press second enter and change the plus to a minus, I get the teeth on the left of the beta 1 trap. So now when you look at the teeth listed in your notes and the teeth that are up here on my calculator, you can see where it is they came from. We're not going to be singing the jingle and going to stat test whatever in order to get these teeth. You have to actually type these numbers in. Then you got the conclusion on the bottom. The conclusion on, hopefully, you know what I'm going to do? I'm going to pull this right into my document so you can look at them both at the same time for you note-taking edits. Okay, so there it is. There's the calculator stuff. The conclusion is based on the sample, we're 95% confident that for each minute added to the length of a movie, the predicted cost of making the movie increases by between 0.41 and $1.02 million. So, in boldface, I put the words that are hard to remember when students are explaining. This is a slightly different wording for the interpretation of a confidence interval. Let's see how it's different compared for each minute added. Yeah, we're trying to trap the slope. And slopes, like the slope of know, 0.51, what's our slope? Our slope is 0.714. But interpreting the t, so suppose we're interpreting 0.408, so that would be 0.408 over 1. So for each additional minute, or for each minute added to the length of the movie, the predicted cost increases. This is an increase of 0.408. So yeah, I'd say that word increases is easy to leave out, but when you realize we're talking about interpreting slope, sure enough, we said for each additional hour of flood duration, first one, we interpreted 2.5 over 1. For each additional hour of flood duration, the depth of the river is expected to increase by 2.5 feet. I think that's the first time we ever interpreted a slope, was that river, I think it was y hat equals 30.5 plus 2.5 x, where x was hours of flood duration, and y was predicted river depth. We said for each additional hour of flood duration, the model predicts an increase of 2.5 feet in river depth. So we see that word increase showing up again because this is a beta 1 trap for the true slope. Okay, well that's that handout. Now let's go to the last handout. Last handout is the 10.5 handout. Let me pull it up right here. And this one is, let's go to page 2 of this thing. And hello, hot dogs. So this is working more with the scripts. And here we see that healthy eating probably does not include hot dogs. What, these narrow-minded people that think that hot dogs have no place in healthy eating. No. Where are you going to get your daily requirement of nitrates, your recommended daily allotment of nitrates if you're not eating hot dogs? But anyway, if you're going to have a hot dog, you'd probably hope it's low in both calories and sodium. They sure are assuming a lot there. In its July 2007 issue, Consumer Reports listed the number of calories and sodium. So here we go. We're predicting sodium. Actually, dependent variable. So we're predicting the sodium from calories. If you know calories, can you predict the sodium? So we got sideways bell curves all over the place. Which one is the standard deviation of the sideways bell curves? Is it 0.5607 or is it 0.5966? 0.5966, that's the standard deviation of the sideways bell curve. So for any particular number of calories, then we would say that the error in predicting the amount of sodium varies, or the error is 59.66 units. Looks like milligrams. So anyway, state the appropriate hypotheses. When we're writing out the hypotheses, those are probably blank on your paper, huh? So null hypothesis would be that there is no association between calories and sodium content of all beef hot dogs. You can't just say hot dogs. It's not all hot dogs. It's only the all beef hot dogs. And the alternate hypothesis is that there is an association between calories and sodium content of all beef hot dogs. Continuing, test your hypotheses and state your conclusion. It's a big paragraph. You might want to take a picture of it. It's actually in the notes that are on Academy Central. It looks like some of you have already discovered this. It's the last day of new material, and you don't have, and here today's the day you discover you didn't really have to take notes because this is all on Academy Central. If you open up the master document for 10.5, then in the second half of that document, you'll find all this stuff. Assuming the conditions have been met, the sampling distribution of the regression slopes can be modeled by a student's t-model with not n-1 but n-2 degrees of freedom. We're going to use the regression slope t-test. The equation line of best fit is sodium hat is B0 plus B1 times calories. The value of t is 4.10. The p-value means that the association we see in the data is very unlikely to occur by chance alone. So notice here, for these p-values, we're not using phrases like the observed value of blank or greater. We don't have to use that phrase of blank or greater for the observed value here. We are talking about observation, saying that here's the eyeball word. We do see an association in the data, and it's by looking at the scatter plot that we see it. There we go. So we do have an eyeball word, and I must be in white. Yep, let's switch to red. So we have an eyeball word, but it's very unlikely to see that association by chance alone. We rejected all hypotheses and conclude that there is evidence of a linear association between the number of calories in all beef hot dogs and their sodium content. So, now, if you're trying to write that down, that's wonderful, but it's on Academy Central, just to look at the second half of the document. Now, let's take a look then at problem number 9. Second Frank. And I'm going to do clear annotations here. Okay. Look again at exercise 7's regression. The output reports that S is this. Explain what it means. Once again, for all beef, instead of saying for movies that are of a particular length, or for all movies that have the same length, we say among all beef hot dogs with the same number of calories. So do you see the parallel construction with what we had on the movie problem? So the sodium content varies with a standard deviation of about 60 milligrams. Here's another way to write it. Among all beef hot dogs with the same number of calories, the typical difference between the actual sodium content in a particular hot dog and the predicted sodium content is 56.66 milligrams. Let's see if my voice will carry to the end. Almost there. Come on, you can do it. I like this blue narrative because it mirrors what we learned first semester about how to interpret a standard deviation. What's the value of the standard error of the slope? The standard error of the slope of the regression line is 0.5607 milligrams of sodium per calorie. The hard part there is going to be to get the units straightened out. But come on, it's right there. You don't have to calculate it, you just have to pick it off of the table. Then finally, explain what that means in context. Here's the hardest one of the day. We've never had to explain the standard. I told you when Caleb was here asking about this number, I said, well, it's the standard deviation of the slopes. How do we put that into words? If we tested many other samples of all beef hot dogs, the slopes of the resulting regression lines would be expected to vary with a standard deviation of about 0.56 milligrams sodium per calorie. That's not a surprise, is it? Once you know, if you listened in on the conversation that Caleb and I were having about the meaning of standard error of the slope, this makes complete sense. I drew a whole bunch of other lines of best fit. Here's one, it has a slope, different lines have different slopes. The slopes of these lines of best fit would be expected, the slopes of the lines of best fit would be expected to vary with a standard deviation of that number. Any questions on this guy right here? Okay, so some of you are taking pictures, some of you are taking pictures and writing notes in case you don't have time to look at the pictures.
It's all on Academy Central.
I'm sorry, what's that?
Is it all on Academy Central?
That's a good question. The stuff in, let's find out. Let's take a look at Academy Central. Let's find out what's actually there. Because it might not, the green stuff might not all be there. It's time to find out. For a second there, I thought maybe the internet had been canceled. Maybe they thought it was a bad idea. It's time to stop using the internet for humans. But no, the internet is still operational, as those of you on YouTube are already experiencing. And when we go to Academy Central, the internet will be unplugged in 3 seconds. 2. We don't have much more time. We better find it quickly. So, AP Stats, what actually is in the 10.5 document? So, we go to AP Stats. We're in Unit 11. Let's take a look at the 10.5 document. 10.5 master. What does it look like up there? I wonder if it has those cool green statements. Here we go. Moment of truth. First half of the document is blank, and Rapunzel, do you need the second half of your thing? And that one's blank, simplify master, oh, scratch that one. Yeah, okay, well, I'll tell you what, you know what I'm gonna do? I'm gonna post this one, since it has so many crucial words on it. I'm gonna post it right, it's gonna be called 10.5 filled in. Deal? Is that okay with you? Do I have your permission? Deal? Okay. I'm gonna post it up there. While you're taking the quiz, I'm gonna post it. So it's quiz time. Wait, no, there's one more problem. It's this one. Last dog. It's come down to the last dog. It's not final hot dog, but it is the last dog. If you know what I mean. Okay, so hot dog problem, I mean, the all beef problem, all beef hot dog problem. Create a 95% confidence interval and interpret your interval in context. So, we use the formula for the beta 1 trap again, and we put in, using inverse normal, rather inverse t of 0.975, comma, 11. That'll give you the 0.2201, and when you identify the teeth, if you calculate the teeth, you get 1.03, comma 3.57. Here's your interpretation. Based on this sample, we are 95% confident that for each additional calorie all beef hot dogs have, on average, the reason we're saying on average is because it's just the average of the sideways bell curve. It's the middle of the sideways bell curve. Between 1.03 and 3.57 more milligrams more of sodium. So, I will post this document right next to it'll be right under the 10.5 master. Okay, happily, we got 40 entire minutes to do the quiz. That's more than humans are actually allowed to have on this quiz.
Mr. Royce, do you need me to go to the other room for?
So, thank you for taking AP Statistics. This concludes the course.